Wonder. Standing at 828 meters, the Burj Khalifa completely dwarfs everything around it. When you look at the Dubai skyline at sunset, the sheer vertical scale of this building feels completely unnatural. In a standard skyscraper, the vertical columns at the base must widen to support the weight of the floors above. At this height, a traditional design would require columns so thick that they would occupy nearly all the usable space on the lower levels, making the building a structural bottleneck. For decades, skyscraper engineering relied on methods like the bundled steel tubes seen here on the Willis Tower. But reaching 800 meters required a departure from this old box-shaped paradigm. When you push a structure past the half-mile mark, you leave traditional architecture behind. Building at that altitude is a direct, physical negotiation with the upper atmosphere. To break the half-mile ceiling, engineers had to move beyond the traditional box and invent an entirely new geometry capable of surviving the environment. The first threat is gravity. Half a mile of concrete and steel creates a staggering amount of weight, and all that mass actively tries to crush its own foundation. But the second, more chaotic enemy is the wind. At extreme altitudes, engineers have to account for a fluid dynamics problem known as vortex shedding. In this diagram, you can see how straight wind interacts with a flat tower. The air currents separate into alternating, swirling pockets. These organized vortices create a rhythmic push and pull, swaying the building side to side. That invisible rhythmic pulling is dangerous. Over time, repeated stress tires out the building skeleton, causing structural steel to fatigue and snap. A tower of this scale must be heavy enough to resist the crushing force of gravity, while its shape must be specific enough to keep high-altitude winds from finding a lethal frequency. The solution starts at the very bottom. Instead of a square footprint, the Burj Khalifa relies on a Y-shaped floor plan. Looking at this blueprint, the anchor is a massive hexagonal core acting as the building's immovable spine. 3 symmetrical wings branch out, continuously pushing inward. Spaced exactly 120 degrees apart, at least 2 wings are always positioned to absorb and redirect wing pressure from any direction. You can see the scale of this geometry during early construction. Sprawled across the dirt, the foundation looks like an enormous 3-pointed star. It functions exactly like a giant tripod. The buttressed core captures the tower's downward weight and spreads it out across the desert floor. With gravity handled at the base, the next step is neutralizing the high-altitude winds as the building rises. Notice how the exterior doesn't rise as a single uniform block. It features distinct asymmetrical steps climbing up the side of the tower. These stepped setbacks serve a precise mechanical purpose. With every new tier, the building is forced to completely change its cross-sectional shape. In this 3D model, straight wind hits the staggered steps and instantly breaks apart into chaotic airflows. The building confuses the wind. By preventing organized swirling vortices, the rhythm breaks. Wind pressure loads drop to safe levels, eliminating the rhythmic stress that causes fatigue. This asymmetrical profile acts as a passive defense, turning the wind's chaotic energy against itself so it cannot find the organization needed to dissuade a tower. These combined countermeasures result in a stable spire that survives in the middle of a desert environment. The structure is stable enough to withstand the explosive force of massive fireworks displays detonating directly off its exterior without any measurable sway. This tower validated a new set of rules for the megatall category, structures exceeding 600 meters that were once thought to be impossible due to the sheer weight of their own materials. The Burj Khalifa proved that the vertical limit is no longer dictated by the sky. Our ceiling is now determined by our ability to invent geometries that can